And so then what you end up with is you can plug that back in, and you end up with dg dt is equal to the activation energy over RT squared times the function itself. And so if we set those things equal to each other, the slopes equal to each other and the functions equal to each other, we have two equations and two unknowns, and we can solve for this tangential point, t. And what you end up with when you do that, I did that last time, so I'll just put up the final equation. And what you end up with for t star and that is specific to a zero order rate equation. Higher order rate equations, it's the same procedure. You just get a different value. You get a different formula for T star as a function of things like the critical temperature and the activation energy. Why is that point important? Why do we care about that point? Actually, you don't have any instability after that. If I'm increasing the temperature, the instability all goes away.
Saying if you go past T star,
yeah, what happened?
Then your tiny jumps from very small change, well, a reasonable change to bang, huge change.
Yeah, I mean that's one way of thinking about it. The temperature of the reactor goes way up, right? So there's another point that's similarly defined that also has two steady states, right? If I draw that curve. And then, of course, I can draw a line at a colder inlet temperature or at a hotter inlet temperature. And so each of those has just a single steady state. And so if we label these points, let's put labels 1, 2 is this intersection, and 3 is the tangential point up here. 4, 5, 6 are the intersections for the next curve. This one, 7 is this tangent point. The upper point there for that curve is 8, and then finally 9. We're just putting labels on these things. And now we're going to make a plot of the inlet temperature versus the steady state temperature. And so what happens as I increase the inlet temperature is you get a steady increase in the steady state temperature, right? 1, 2, sorry, these numbers are wrong. 1, 2, 4, 7. And then at the same inlet temperature, do we have a high temperature steady state for this first point? No, right? That's stable. What about the second point? Yeah, so there's this point up here is the third temperature. We have a point up here, which is the 6th. 3, 6, 8, 9. 8, 9. We're missing 5. It'll show up. So what do we call this point? What's another name for it? Or what is this process? What happens right here? What do we call that? It is a discontinuity, but it's often referred to as ignition. So this is the ignition point of the reactor. If I go to a slightly higher temperature, the temperature of the reactor shoots, for my feed, the temperature of my reactor shoots way up. And this line is called extinction. And this is the extinction temperature is T3, which is the other tangent point, right? We have this one tangent point. On the bottom end, there's another tangent point at the top end. So where is 5 on this plot? In between 4 and 6, like it is everywhere else. Is 5 stable? No, and you know that because I told you last time. But now let's try to think about why is it not stable. This curve is getting crowded, so I'm going to do another one over here. Okay, so this is G and this is R. And remember, that's heat generated and heat removed. So if I'm at 5 and for some reason the temperature goes up a little tiny bit, what happens? I move this direction and now suddenly I'm at this line. What's the difference between heat generated and heat removed? Which one's larger? I'm generating more heat than I'm removing. So what happens to the temperature? It continues to increase. Until when? Until the amount of heat generated is again equal to the amount of heat removed. That's my other steady state solution. So if I'm at 5 and I experience a little perturbation, it's going to very rapidly go to that higher steady state temperature. Similarly, what happens if I'm at 5 and I get a little bit colder? Now which is higher, removal or generation? So I'm removing more heat than I'm generating. What happens to the temperature? It continues to go down until what? I hit this point, which is 0.4 on the other plot. Let's contrast that now to if I'm at 0.6. What happens if I add a little bit of heat, but I'm at 0.6 instead of 0.5? I go up a little bit, but now which one's higher, removal or generation? Removal, so what happens? I get colder. I go right back to where I started. And so that's the difference between a stable steady state and an unstable steady state, is that if some perturbation occurs around a stable steady state, these two functions are going to force me back towards T6. Whereas in this case, the functions are going to force me away from T6. So, excuse me, T5. One's gonna, yeah.
You can still operate at T5 with the process control.
You can operate at T5. It's a steady state solution. It's just not stable. Meaning that if you have a perturbation, cross your fingers. You have to be very, very careful about the size of the perturbation you can tolerate before it's going to run away. Or like you're mentioning, if you have a controller, it sees that you're a little bit too hot. It increases the amount of heat removed from the system by, for example, increasing the mass flow rate of your cooling fluid. And yeah, those systems exist, but you wouldn't want to build a system around it. So any questions about this, about why that point is stable versus unstable? Yeah?
So if you want to operate at 6, would you always be on the safe side and keep it a little bit warmer than it should be?
At 6? Well, no, because if I get colder, the opposite happens. If I'm colder than 6, G is greater than R, so my temperature is going to go up. It's going to push me right back to 6. In either direction, it's going to push you to 6.
Oh.
Right? I mean, think about it. Here, I'm a little bit too, I'm removing too much heat, so it's going to cool. But here, I'm generating too much heat, so it's going to heat. So either way, I'm getting pushed towards 6. That's what makes it a steady state solution. A stable steady state solution. So mathematically speaking, how can I put that into some mathematical expression to determine whether or not a solution is steady or unsteady, or stable or unstable?
Place R in
Say that again?
The derivatives tied together.
All right, so you want to look at the sum of the derivatives, maybe, but you're right. I mean, in the sense that it is the derivatives that matter. So let's look at this point. What are the differences in the derivatives? If I'm comparing those, what do I put here?
Smaller.
Right. No, not equal. They're not. This isn't a tangent point.
Oh.
You're thinking of the tangent point. At this point, as you can see off the board, the slope of G with respect to temperature is smaller than the slope of R. What about at 4? Is it any different? So this is true at both points 4 and 6. What about at point 5? This is the criteria. If the slope is less, then you have a stable solution. If the slope is more, then you have an unstable solution.